Alrighty, how are you all doing this morning?
Doing all right.
Cool deal.
Doing good.
Let's see. So I think the material that I posted for you guys to look at was using the practical op-amp model to solve a negative feedback op-amp circuit. So did anybody have any questions about that bit of it? All right, nobody's saying much of anything, so that's good. So one thing that I noticed last quarter is that students on the homework set associated with negative feedback op-amps, they didn't really understand how to apply the ideal model correctly, which seemed odd to me because it's a much easier thing to apply. So let's work a couple of examples of applying the ideal op-amp model, which is exactly what we did in circuits 1, by the way. So that's why I'm very confused as to why people didn't really understand how to do it, because they've already done it before, but whatever. So actually, let me think. Yeah. What I'm going to do is I'm going to find an old circuits 1 test problem that uses the ideal op-amp model, and it's kind of ugly and nasty, and we'll use that to go through things. Let's see. $221. Let's see how mean I was in the spring of 2018. Not horrifyingly mean. Okay. Sorry, my tablet's going crazy. Wanting to rotate and all kinds of jibber jabber that I don't want it to do. So this is the circuit that I gave on this test a couple of years ago. Honestly, it's probably a little meaner than I would do today, which is good news for you guys. Let's let's see, and this is 15 volts, but it's going to illustrate everything I want to go over with regards to how to apply the ideal op-amp rules. So the ideal op-amp rules are that there's no potential difference between the input terminals. So that means that this differential voltage here between the non-inverting terminal and the inverting terminal is 0 volts. And I realize that I drew the polarities. So typically speaking, the positive polarity is associated with the non-inverting input terminal. But when it's 0 volts, it doesn't really matter which polarity I choose. So I just did top to bottom. The other ideal op-amp rule is that no current can flow into or out of the input terminals. So we know that the current that's flowing into the op-amp itself must be 0. One important thing to note is that the current that's flowing out of the op-amp can be whatever it needs to be using the ideal op-amp model. So there's no restrictions there. All right, so since you biomed students probably have more experience solving op-amp problems than my EE students, I'm going to ask you guys to not chime in for a minute and ask if any of my EE students could tell me where to start on this problem.
Do you have to solve for the voltage at the positive polarity terminal?
That's exactly right. So our first step should pretty much always be solving for the voltage at the non-inverting terminal. So that voltage is with respect to ground, measured with respect to ground always. So the voltage that we're looking for, let's use this color, is essentially the voltage drop over the 6 kilo ohm resistor, because the positive polarity terminal of that is connected to the non-inverting input and the negative polarity terminal is connected to ground. So that is by definition the voltage drop at the non-inverting input with respect to ground. So any ideas on how I might get that voltage value?
Well, if no current can flow into the op-amp, then all the current from the current source is going to ground, right?
Right, so all the current from the 4.5 milliamp source will flow through the 8 kilo ohm resistor, and then it can't split off, so all of that 4.5 milliamps must also flow through the 6 kilo ohm resistor. So 4.5 milliamps times 6 kilo ohms, let's see, that's going to be 24 plus 3, should be 27 volts if my mental math is correct.
Yep, that's what I got.
All righty. Now that we know that voltage, applying our first ideal op-amp constraint that there's no voltage drop across the input terminals, that means this voltage at the inverting input terminal must also be 27 volts, right?
Yep.
Okay, so what can we do from here to figure out what our output voltage is?
We could do nodal analysis, see how much current is passing through that 7 kilo ohm, and then find the voltage drop over the 3 kilo ohm resistor.
Yeah, that's absolutely right. So if we do nodal analysis at the non-inverting input terminal, where we're going to be summing, so this current is leaving, this current is leaving, and this current is leaving. So if we add all three of those together, we should be able to get a relationship that will tell us what V out is, right? So using nodal analysis, the current flowing through the 4 kilo ohm resistor could be expressed as, 27 volts minus 15 volts, positive 15 volts because I see the positive polarity terminal of the 15 volt source, divided by 4 kilo ohms, plus 27 volts divided by 3 kilo ohms. That's the current directed to the left through the 3 kilo ohm resistor, plus 27 volts minus V out divided by 7 kilo ohm resistor is equal to 0. So I have one equation, one unknown, so let me find a calculator real quick. Use my numerical solver. So let's see, 27 minus 15 is 12 over 4,000 plus 27 over 3,000 plus 27 minus x, our unknown, divided by 7,000 is equal to 0. I get V out is equal to 111 volts.
Yep, that's what I got as well.
Cool deal. So this was a kind of ugly, gnarly looking circuit, but just using those simple rules and nodal analysis techniques, we were able to solve it. And honestly, we can use that for any negative feedback op amp. That's all, negative feedback op amp circuit. That's all you'll ever need to go through it. So the next lecture materials that I have posted are on common negative feedback op amp topologies, which should be a review from what you did in circuits 1. So like the inverting amplifier, non-inverting amplifier, summing amplifiers, differencing amplifiers. Depending on who you had, you may have had integrating and differentiating amplifiers, or they may be new, so you can do calculus with op amps as well. But it's all based on just these simple applications of the ideal op amp rules and then doing nodal analysis. And when we do cascaded op amps, I guess that would be next Tuesday, that's where we string multiple op amps together. It's still this basic process. It's just identifying the voltage at the non-inverting input terminal, mirroring that voltage at the inverting input terminal, and then performing nodal analysis at the non-inverting input terminal to figure out your relationship to your output voltage. The steps are the same for all negative feedback op amp circuits where you're using the ideal model. So does anybody have any questions?
I have questions, but not related to this material.
Okay, what are your questions?
So for homework 2, when we're asked to verify something in LT Spice, what exactly do you want us to provide? Like, is it fine to just provide the trace, or do you want the actual diagram as well?
Oh, so for when you submit stuff, if you're going to give me, so whenever I ask for verification, I would always like to see both your schematic diagram as well as your plot.
Okay. And for homework 3, I'm having trouble modeling the, for the first problem, I'm having trouble modeling that op amp in LT Spice.
All right, let me pull up homework 3 real quick. All right, so by that op amp, which op amp are you referring to? Problem 1, problem 2, or your design?
Problem 1.
Okay, problem 1. So let me stop sharing here and find LT Spice on this computer. There we go. Out of the way. All right, so we are going to need universal op amp. I have to connect my keyboard. Right. Right, and let's see. I'm gonna have, actually, I should have rotated that twice. Let me see. Yeah, I'll just run the feedback loop the other way around. That'll be fine. I'm gonna have a resistor. Just a second, I'm gonna drive myself nuts if I don't have the mouse connected to this thing. All right. So there is my feedback resistor, and then I'm gonna have another resistor out over here. Let's wire these guys up. Output voltage. To be my input voltage. This guy is going to be my reference voltage. And then let me set up all my power supplies. So that's my power supply voltages. This will be my reference, and this will be my input. All right, now I need to put all my component values in. So this resistor is a 15K. This resistor is a 25K. My power supply voltage are plus and minus 10, so I do 10 here. Sorry, my dogs are going berserk. My reference voltage is 1.5 volts. And let's see. Let's have my input voltage swing from minus 10 to positive 10. So we'll make it a sine function, amplitude of 10 volts, and frequency of 1 hertz. And let's look at it over 3 cycles. There's my input. There's my output. And I'm going to change this guy to be plus and minus 12 so I can actually see it clip. So I guess that's how you do it. I don't know what problem you were having, but that's how I do it.
Okay, I think I was telling it to trace the wrong value because whenever I would set it up, I was doing it to where I would use the horizontal axis and put the voltage in there, and I just got some absolutely crazy graph that made no sense.
Okay, so you may think it makes no sense, but it actually does. So let me delete my input trace there, and then put the in here. Let's see. Let me move this out of the way. So this is an example. Is this similar to the graph that you got?
Yep, that's the exact graph.
Okay, so this is a hysteresis loop, which you may not be familiar with yet, but effectively, and it's going to be hard. Let's see. Can you see my cursor? Let's start there.
Yes.
Okay, so what's happening here is this voltage is effectively at its low value until it hits, I guess, something around 8.4 volts looking at it, at which point it swings up to positive saturation, and then it's going to stay at positive saturation until it reaches 10 volts. When the voltage goes back down, it's going to stay up at 10 volts until it hits the lower trigger limit, which looks to be around negative 3 point something volts. And then it's going to go down and it's going to stay at negative saturation as it goes back. So it's just making this path over and over and over again as the voltage ranges from negative 10 to positive 10 and then back down from positive 10 to negative 10. So this is actually describing exactly what we want it to see, just in a different way. And so this would be our lower trigger limit. Whatever voltage this occurs at is the lower trigger limit, and whatever voltage this occurs at is the upper trigger limit.
All right, that makes sense.
So it's we get this odd looking graph because there's what's called latching. So it's holding on to a value until a certain trigger limit is reached. And we didn't see this in our comparators because the comparator effectively doesn't have any memory. That positive feedback is providing a means for this op-amp circuit to hold on to a particular value until a specific criterion is met. So, oh my gosh, my dogs are driving me nuts. Okay, so for this particular problem, you could give me a hysteresis loop like this for your result, or you could give me the time domain plot where you're just plotting an input signal and the output signal together versus time. As long as I can clearly see that it's triggering to the positive limit whenever you're at or beyond your upper trigger limit, or whenever it goes down to your lower trigger limit because your voltage is less than or equal to the lower trigger limit, I'm fine. Doesn't really matter which way you show it to me.
All right. Looks like I'm going to have to go back and redo most of these anyway because I didn't include the diagram.
Okay, yeah, I like to see that. I don't know, like you could save the plot and send it among each other and it's all going to look exactly the same, but your actual schematics, hopefully you won't have the components placed in the exact same areas so that you can't just send the file to each other. Yeah, at least try to make cheating hard.
And so for the same homework problem 2, can we just set up a schematic like that to see if our V outs are correct?
Yeah, so for problem 2, it's going to be an inverting Schmitt trigger because the input is on the inverting terminal. So yeah, you'd set up the schematic pretty much the exact same way. The only difference is where you put your reference voltage versus where you put your input voltage. So Vref would be on the pin connected to what would be the 5 kilo ohm resistor, but what is currently the 15 kilo ohm resistor in the schematic that I have drawn. And then Vn would be placed where Vref is. And I don't remember whether or not I derived the relationship for an inverting Schmitt trigger in the lecture or anything like that. But if you'll notice, it's literally the exact same circuit, except Vn and Vref are transposed. And so the circuit analysis should work out that way as well. So the circuit analysis that I did for the non-inverting Schmitt trigger, where I could get the relationship, if you literally switch Vn and Vref, that's all you need to do to figure out how an inverting Schmitt trigger works. Any other questions about homework 3 or any other homeworks or anything like that?
Not that I can see. I'm just a little confused about what you meant for problem 2, the one where they like give you all the values and everything, and you solve for V out.
Problem 2 of homework 3?
Oh, homework 2, I'm sorry.
Okay, let's see.
I'm just wondering if you can model it exactly as it's seen.
Okay, let me look at that real quick. So for problem 2, okay, so homework 2, which problem did you say?
Homework 2, problem 2.
Okay, so for homework 2, problem 2, what I would do is create a single op-amp, practical op-amp model circuit. So let me circle back to, like, this is one where using LT Spice probably isn't the best move, because your LT Spice model of your practical op-amp isn't going to be able to apply the saturation distortion correctly. So we're gonna have, let's see, something like this. And so V1 is connected to the inverting input terminal. So this is where your voltage V1 is applied. And this is where your voltage V2 is applied. Then you have AV times VD, R out, RL, V out, and this is your ground plane. So this is the output side of this guy is effectively just a simple voltage divider circuit where V out is going to be AV times VD multiplied by RL divided by R out plus RL. So this is going to be AV multiplied by VD is V2 minus V1 RL over R out plus RL. So this is how you could determine the output voltage for literally every single one of these different configurations. You put in your open loop gain for AV, plug in the values for V2 and V1. RN never actually shows up, which nothing wild there. Put in your value for RL, put in your value for R out, and if your answer is greater than the power supply voltage, so if it's more positive than the power supply voltage that I have listed of 18 volts, it's going to saturate to positive 18 volts. If it's more negative than the negative power supply voltage of minus 18 volts, it'll saturate to negative 18 volts, and that's it. So this is all the circuit analysis you would need to do. At this point, it's just plugging stuff in.
All right. It's just that I got like really small values, so I wasn't sure of my answers.
Yeah, so I mean, so let's see. For part A, your voltage gain is 200 volts per millivolt, so that's the same as 200,000. Your differential voltage is negative 10 microvolts. So let's see. 2 times 10 to the 5 times negative 10 times 10 to the minus 6. RL is 1 kiloohm divided by RL plus R out, so 1075. So for part A, my answer is negative 1.860 volts.
Okay, yeah, that's what I got.
If I recall correctly, so let's see, for part B, a voltage gain, or excuse me, an open loop voltage gain of 120 decibels is the same as 1 million volts per volt. So that gain's really, really high. So we're going to have a million is 10 to the 6. $75 minus 5 is 70 times 10 to the minus 6. Let's see, 5,000 divided by 5,015. So you get an answer for part B of 69.7906 volts, which is higher than the positive power supply voltage, so it'll saturate to 18 volts.
Okay, I did that one wrong. I guess I got tripped up on converting the decibels. Yeah,
sorry.
the gain is what I'm having like trouble with because I don't think I've had to deal with this before.
Yeah. So a decibel is, how you find that is 20 log V out over Vn, where V out over Vn is the voltage gain.
All right. And that's just for converting decibels?
Yeah.
Okay.
This is the definition of how you get a decibel. So 120 decibels means you're going to have a specific voltage gain. So if we did 20 log of a million, got to find the log button on my calculator. We get 120 dB. Yeah, sorry, I didn't realize you guys hadn't had to deal with decibels yet. And then
Yeah.
on the third one, volts per volt's easy, so you don't even have to do any conversion whatsoever.
And for the first one, you said it was 200,000?
Yeah, because it's a volt per millivolt, and a volt is 1,000 times larger than a millivolt.
Okay.
So that's why it's 200 multiplied by a factor of 1,000.
Oh, okay. I did it wrong, but I did my calculations in MathCAD, so MathCAD did it correctly. All right. I see how that worked out now.
Alrighty, any other questions?
Thank you for fixing that Zoom link for me, Dr. Hartman. I appreciate it. And also on the homework, do we need to include a math pad for each problem?
Only if you use MathCAD for the problem. So if you're able to do it on your calculator, then that's fine. But a lot of problems are going to require solving systems of equations greater than 3 equations, 3 unknowns. So the expectation is you're going to be using MathCAD quite a bit.
Okay, got it. Thank you.
Mhm. Any other questions? All right. Well, nobody's saying much of anything. I think personally we're actually at the pretty easy part of op amps for the next couple of days. So classes or whatever will probably be pretty short. Unless you guys want me to expand on stuff, I got no problem doing it. But anyway, I guess have a good weekend, and I'll see you guys next Monday morning.
Thank you.
Dr. Hartman, just a quick question.
Yes, ma'am.
I just to clarify, is it lecture 5 that we'll be covering on Monday or is it, or am I behind in a lecture? I'm just kind of.
No. So my first lecture, I guess, was when I was talking about the syllabus and going over the stuff. So you're caught up.
Okay, I just wanted to make sure before we go in class that I was like in the right spot while
Right.
studying.
Yeah, let me look at the web page for the course real quick to make sure I haven't put stuff in dumb things. So this is class meeting 4. And so the material that you were supposed to look at today was the ideal lecture for ideal amplifiers and all that kind of jibber jabber. So class meeting 5 is common negative feedback op-amp circuits. So that's what you're supposed to cover for Monday. It's a review of what we covered in circuits 1 regarding all those different types of negative feedback amplifiers. And then the homework assignment 4, I believe. So like the first problem asks you to do, to solve this circuit for the output voltage using the practical op-amp model. And then after that point, everything is using the ideal op-amp model. Yeah, that's right.
Okay, thank you for clarifying. I just wanted to double check.
Yeah, and I'd be willing, I don't know how many of you have looked at things yet, but I'd be extraordinarily surprised if none of you had questions regarding the design problem associated with homework 4. So just a heads up, it's maybe a little more difficult than it looks at first glance. So we'll probably talk about that a little bit on Monday before we jump into any questions or anything you guys have.
All right, thank you.
Yep. Any other questions or anything? All right, well, catch you guys on Monday. Have a good weekend.